as the world has surpassed 8 billion people. Yet only about 11% of the Earth's land area is suitable for cultivation. Humanity is doing something bold, bringing agriculture onto the water, underground, into containers, and even into high-rise buildings. From floating dairy farms in the middle of seaports, leafy greens growing 33 meters beneath London, and tomatoes thriving under intense sunlight and seawater, to 26-story pig farming buildings in China, modern agriculture is entering an era unlike anything we have seen before. So what is forcing agriculture to change in such unusual ways? And are these models the future of food, or simply expensive technological gambles? Today, join Terran Works as we explore the story behind the strangest farms on Earth. For most of human history, agriculture relied on three basic elements: land, water, and a stable climate. But in the 21st century, all three have become increasingly unpredictable. Land near cities is becoming more expensive, while farmland must compete with housing, industry, renewable energy, and infrastructure. Even many wealthy countries still depend on imported food, meaning that just one shock in transportation, disease, war, or fuel prices can disrupt the supply chain. At the same time, the climate is making outdoor production riskier. Droughts, heat waves, floods, and saltwater intrusion are forcing many countries and businesses to ask a new question. If traditional fields are no longer stable enough, can agriculture be moved into more controlled environments? That is why unusual farming models have begun to appear. In the Netherlands, floating farms help adapt to urbanization and the risk of flooding. In London, vegetables are grown inside old air raid shelters. In Australia, greenhouses use sunlight and seawater to produce fresh water for crops. In Singapore, where farmland is scarce, vegetables are brought onto rooftops and into closed-loop systems. And in China, the pressure to produce meat on a massive scale has pushed livestock farming into high-rise buildings. These models may differ in form, but they all answer the same question. If the future no longer gives agriculture more land, where will humans find land to farm? The story begins in Rotterdam, the Netherlands, one of the largest port cities in Europe. Among ships, warehouses, containers, and industrial cranes, around 32 to 40 dairy cows are living on a floating farm in Merwehaven Harbor. This is not a showcase model, but Floating Farm Rotterdam, the world's first floating dairy farm, capable of producing around 800 liters of milk per day right in the heart of the city. What makes this model special is not only the image of cows standing on the water. The Netherlands is a country that has lived with water for centuries, with its famous system of dikes, pumps, and reclaimed land. So the floating farm is not simply a strange idea, but a way for the Dutch to turn water, once their greatest challenge, into a new space for agriculture. Inside the farm, the cows are kept in a covered space, using an automated milking system, waste cleaning robots, and a circular process. Part of their feed can come from local byproducts, while the milk is produced closer to consumers, instead of being transported from rural areas far from the city. Of course, this model cannot yet replace the traditional dairy industry. Some sources have estimated the construction cost of Floating Farm Rotterdam at around 3 to 4.7 million USD, a very high figure compared with its scale of only about 32 to 40 cows and a daily output of around 800 liters of milk. From the waters of Rotterdam, the story moves straight down into the underground of London. Beneath the Clapham area, at a depth of about 33 meters, an air raid shelter once built during World War II is being transformed into a hydroponic farm. Here there is no sunlight, no rain, and no natural soil. Trays of pea shoots, coriander, thyme, and various microgreens grow with water, nutrient solutions, and precisely controlled LED lighting systems. Across a growing area of about 550 square meters, this model has reportedly been able to produce around 20,000 kilograms of greens per year. A remarkable figure for a farm located entirely underground. What makes it special is that two almost opposite worlds are stacked on top of each other. Above is crowded London, with trains, vehicles, offices, and a rhythm of life that never stops. Below, inside old tunnels once forgotten by the city, rows of vegetables continue to grow quietly under artificial light. A piece of wartime infrastructure, instead of being abandoned, has been reborn as part of urban food security. Of course, an underground farm cannot replace fields of wheat or corn. It consumes electricity, requires a high-value market, and is only suitable for short-cycle crops. China is experimenting with a model that has stunned the world, turning high-rise buildings into massive pig farms where each floor operates like a closed livestock unit. Located in Ezhou, Hubei province, this 26-story structure has been described as one of the largest pig farms inside a building in the world, with a capacity of around 1.2 million pigs per year. When it began operating, the facility brought in about 3,700 sows, showing that this was not a small experimental model, but a large-scale move within China's pork industry. In terms of technology, each floor functions almost like a closed farming unit, divided according to different stages such as breeding, pregnancy, farrowing, piglet rearing, and fattening. Automated systems control feed, water, temperature, ventilation, waste, and disease monitoring. Feed can be transported through pipes or automatic distribution systems, while sensor data helps monitor the environment inside the building. The goal is to increase output on the same area of land, reduce direct contact between humans and animals, and strengthen biosecurity after disease shocks in the livestock industry. What makes this model special is also what makes it unsettling. The more enclosed, larger, and more automated a building is, the more efficient it can be when everything operates well. But if problems occur with disease, ventilation, waste, or power supply, the risks also become more concentrated. That is why the pig skyscraper raises questions not only about productivity, but also about animal welfare, the environment, and the degree to which food production is being industrialized. Leaving behind China's controversial high-rise livestock model, the journey continues to a different kind of experiment, bringing crops into an arid region with almost no fresh water. This is Port Augusta in South Australia, where Rooftop Farms grows tomatoes using intense sunlight and seawater. The facility covers about 20 hectares and consists of multiple climate-controlled greenhouses. Seawater is pumped from Spencer Gulf through a pipeline about 5 kilometers long, then sent into a desalination system to produce fresh water for irrigation. At the same time, around 23,000 mirrors concentrate sunlight onto an energy tower more than 120 meters high, generating heat and power to operate the system. Each day, this technology can turn about 1 million liters of seawater into fresh water, supplying the tomato rows inside the greenhouses. Inside, the tomatoes do not grow in natural soil, but in a hydroponic system, with their roots receiving water and nutrients through coconut fiber substrate. Temperature, humidity, light, irrigation, and nutrition are all controlled so the plants can grow steadily throughout the year. Thanks to this, from an arid landscape, Rooftop Farms has reportedly been able to produce more than 15,000 tons of tomatoes per year, equivalent to about 15% of Australia's tomato market. Of course, this is not a magic solution that can turn every desert into farmland. The project has been mentioned with an investment of around 200 million Australian dollars, while desalination, greenhouses, and the handling of excess brine all require complex technology. But Rooftop Farms shows a highly noteworthy direction. In a drier future, agriculture does not necessarily have to drain groundwater to survive. It can learn to use sunlight and the sea themselves to create growing conditions. If Australia lacks fresh water in arid regions, Singapore lacks land. This island nation imports more than 90% of its food and has less than 1% of its land allocated to agriculture, which makes every square meter in the city increasingly valuable. Instead of expanding farmland horizontally, Singapore has begun looking upward. to the rooftops of factories, industrial estates, and commercial buildings. Comcrop is one of the most representative examples. Founded in 2011, it has been described by the Singapore Food Agency as Singapore's first commercial rooftop farm, using hydroponic technology to grow pesticide-free vegetables and herbs. In Woodlands, one of Comcrop's projects covers about 36,000 square feet, with 6 rooftop greenhouses using automated systems to grow fresh produce for the local community. What makes this model special is that the vegetables do not need soil. The plants are placed in hydroponic channels, with their roots receiving circulating water and nutrient solution through pipes. The greenhouses help reduce the impact of heavy rain, intense heat, and pests, while irrigation, water pumping, and nutrient control systems allow the crops to grow more steadily on the city's concrete rooftops. Below are vehicles, warehouses, and offices. Above are rows of green vegetables growing in the air. Of course, rooftop farming cannot replace vast agricultural regions. Rooftops must be able to bear the load, require waterproofing, operational safety, and heat control. But for Singapore, the goal is not to grow all of its own food, but to increase the resilience of its food system. When there is almost no land left to expand, rooftops become a new layer of farmland, smaller than open fields but closer to consumers and less dependent on distant supply chains. If rooftop farms turn rooftops into vegetable fields, then container farms push that idea even further, shrinking an entire farm into a steel box. From the outside, it looks like nothing more than a shipping container about 12 meters long. But once the door opens, inside is a closed farming system with multi-layer growing racks, LED lights, hydroponic systems, ventilation fans, and sensors for temperature, humidity, CO2, and nutrients. What makes this model special is that vegetables no longer need open fields. Leafy greens, herbs, microgreens, or strawberries are grown vertically in a controlled environment. Plant roots receive circulating water and nutrient solution through the hydroponic system, while LED lights replace sunlight. Many modern container farms can operate year-round, creating a stable environment regardless of whether it is hot, raining heavily, or suffering from urban pollution outside. In terms of figures, a standard agricultural container usually has a floor area of only about 30 square meters, but thanks to vertical stacking, its actual growing area can be many times larger. Some commercial manufacturers have promoted that a 40-foot container can produce a vegetable yield equivalent to a small portion of an outdoor farm, while using far less water thanks to its recirculating system. This turns the container into a food production module that can be placed next to restaurants, supermarkets, schools, residential areas, or industrial zones. Of course, container farms cannot replace open fields. They consume electricity, require environmental control equipment, and are only suitable for high-value, short-cycle crops. But the idea they open up is highly noteworthy. In the future, part of agriculture may be standardized, packaged, and placed right in the heart of cities, like a piece of biological production equipment. From the floating farm in Rotterdam and China's pig farming skyscraper, to the vegetable rows beneath London, seawater greenhouses in Australia, Singapore's rooftops, and container farms, all of them show that agriculture is moving beyond the traditional field. In a world where land is becoming increasingly scarce, the climate is becoming more extreme, and food supply chains are more vulnerable, these unusual farming models may become part of the answer to the challenge of producing food in an increasingly unstable world. Israel is one of the most naturally challenging countries in the world for agriculture. More than 60% of its territory is covered by the Negev Desert, where many areas receive less than 100 millimeters of rainfall per year, even lower than some desert regions in the United States. During summer, temperatures can exceed 45 degrees Celsius, while evaporation rates are far higher than the actual amount of rainfall. Unlike agricultural superpowers blessed with massive rivers or abundant freshwater resources, Israel has very limited natural water supplies to rely on. Much of its land is dry, nutrient-poor, and affected by salinity, turning farming into a true fight for survival. For decades, prolonged droughts caused repeated crop failures, drove food prices sharply upward, and placed enormous pressure on the economy of this young nation. With a rapidly growing population and the constant risk of trade isolation in a politically unstable region, Israel understood that it could not depend entirely on imported food. In many parts of the country, water is considered even more valuable than fuel because it determines whether a community can survive at all. And it was precisely this extreme pressure that pushed Israel to create one of the boldest agricultural revolutions in the world. For centuries, agriculture around the world relied mainly on flood irrigation, pumping massive amounts of water across entire fields in the hope that crops would absorb enough moisture to survive. But under the harsh climate of Israel, that method was almost a disaster. Under temperatures exceeding 40 degrees Celsius, huge amounts of water evaporated almost instantly before reaching plant roots, while the rest either seeped deep into the soil or flowed away as waste. That was when Israel developed a system that would transform global agriculture: drip irrigation. Instead of watering the entire field, thousands of tiny emitters deliver water directly to the exact location where roots need it most. Every drop is carefully controlled, reducing water loss by tens of % and turning dry, barren land into farmland capable of producing fruits and vegetables year-round. Israel did not try to conquer the desert with more water. It conquered it with precision. The system quickly spread to many arid regions around the world, from Africa to the western regions of the United States. Today, drip irrigation is considered one of the most important water-saving technologies in the history of modern agriculture. But for Israel, delivering water precisely to plant roots was still not enough to defeat the desert. The bigger challenge came from the surrounding environment itself. Extreme heat, hot winds carrying dust and sand, and insects capable of destroying crops within a short period of time. That is why the country began building massive enclosed greenhouse systems where nearly the entire growing environment could be controlled. Inside structures covered with glass and specialized polymer films, temperature, humidity, lighting, and water supply are all regulated by automated systems. Protective mesh layers and shielding membranes prevent insects from entering, reducing the need for pesticides, while misting and ventilation systems keep crops from being burned alive under the brutal desert climate. What is truly remarkable is that these greenhouses have transformed land once considered almost useless into highly productive farms capable of growing tomatoes, melons, peppers, and leafy vegetables year-round. Some facilities even achieve yields several times higher than traditional farming while using significantly less water. Instead of trying to change the desert climate itself, Israel created an entire artificial world where crops are protected and optimized down to the smallest detail. In many areas of the Negev desert, clusters of modern greenhouses can now be clearly seen from above, like technological oases scattered across an endless sea of sand, something that would have been considered nearly impossible just a few decades ago. As agriculture entered the age of data, Israel pushed its battle against the desert to an entirely new level. Across many farms in the country today, sensors are inserted directly into the soil to continuously monitor moisture levels, temperature, nutrient concentration, and even crop growth rates in real time. All of this data is then transmitted to AI systems that analyze the information and automatically determine when crops need irrigation, how much water is required, and exactly which areas are lacking moisture. In many farms, humans are no longer the ones deciding when irrigation should begin. Drones and AI-powered cameras constantly fly above the fields, detecting heat stress or water shortages before the human eye can even notice the signs. This dramatically reduces resource waste, prevents over-irrigation, and increases productivity under harsh climate conditions. In Israel, water is no longer managed by experience alone. It is controlled by data. Some systems are even capable of predicting water shortages days before plants begin showing signs of wilting, allowing farmers to react earlier and avoid major crop losses during extreme weather conditions. But perhaps Israel's boldest solution lies in something that much of the world still considers waste: domestic wastewater. While many countries continue to discharge most used water into oceans, rivers, or lakes, Israel built an enormous system to collect, treat, and return this water back to agriculture. Inside advanced treatment facilities, wastewater passes through multiple stages of biological filtration, bacterial removal, and impurity treatment before being pumped through hundreds of kilometers of pipelines to farms across the country. Today, Israel reuses around 80 to 90% of its domestic wastewater, the highest rate in the world and far beyond that of most other developed nations. This system significantly reduces pressure on the country's extremely scarce natural water resources. Although using recycled water to grow food once sparked major controversy and safety concerns, Israel viewed it as an almost unavoidable choice for survival. In its view, in a world facing an increasingly severe water crisis, wasting even a single drop of water is the real luxury. Beyond agriculture, many of Israel's water treatment technologies are now being exported to dozens of countries facing worsening water shortages driven by climate change. From a country where more than half of its territory is desert, Israel has transformed itself into one of the most astonishing high-tech agricultural powers on Earth. Today, this nation of only about 22,000 square kilometers not only produces most of its own food supply, but also exports fruits, vegetables, and agricultural technologies to dozens of countries worldwide. Lands that were once barren, rocky, and dry are now covered with greenhouses, smart farms, and precision irrigation systems operating almost entirely through automation. Even more remarkably, Israel is now home to hundreds of agri-tech startups and is often described by experts as the agricultural laboratory of the world. Technologies developed here are being used everywhere from California to Africa and some of the most drought-stricken regions on the planet. While many countries continue struggling with water shortages and climate change, Israel has turned the pressure of survival itself into a global competitive advantage. It did not make the desert disappear. It turned the desert into a massive food production machine powered by technology. Today, many experts see Israel as a model for agriculture in the age of extreme climate, where data, technology, and resource optimization are becoming just as important as land and natural rainfall. What is drawing particular attention from the world is that what is happening in Israel increasingly resembles the future that many drought-stricken states in the United States may soon face, especially Arizona. This desert state is currently experiencing one of the worst water crises in its history, as water levels in the Colorado River continue to decline after years of prolonged drought. Major reservoirs such as Lake Mead have fallen to record low levels, while extreme heat and rapid urbanization continue placing enormous pressure on regional agriculture. And that is exactly why Arizona has started looking at Israel not simply as a successful agricultural nation, but as a survival model. Technologies such as drip irrigation, soil moisture sensors, water recycling, and smart greenhouses are now being adopted by many farms across the United States to prepare for a future defined by water scarcity. The alarming reality is that what was once considered technology built for Middle Eastern deserts may soon become essential across the American West. In a rapidly warming world, Israel may no longer be the exception, but a preview of the future. In many U.S. climate reports, Arizona is frequently identified as one of the regions most at risk of severe water stress over the coming decades if global temperatures continue to rise. If Arizona reflects the future of arid desert regions, then California shows how even an agricultural empire can fall into a severe water crisis. This single state supplies more than 1/3 of America's vegetables and nearly 3/4 of its fruits and nuts. Yet the entire system depends on increasingly shrinking water sources from the Sierra Nevada and the Colorado River. During extreme drought years, hundreds of thousands of hectares of farmland in California were left abandoned because of water shortages, while many regions were forced to pump groundwater at alarming rates just to save crops. That is why more and more companies and farms across California are beginning to adopt technologies from Israel. From drip irrigation systems and soil moisture sensors to AI-powered water management, solutions originally designed to help Israel survive in the desert are now becoming essential tools for keeping America's largest agricultural economy running. What makes this especially striking is that California possesses far greater land area and resources than Israel, yet it is now learning from a small country with almost no natural agricultural advantages. For many experts in the United States, Israel is no longer simply a Middle Eastern nation with an unusual farming system. It is becoming a preview of the future California itself may have to face.
When people think of the harshest places on Earth, they often picture the scorching Sahara or the icy Gobi. Yet in southwestern Africa lies a land even more extreme than both, the Namib Desert, a landscape that has shaped the entire climate of Namibia. Stretching over 2,000 kilometers along the Atlantic coast, the Namib receives almost no rain year-round, with annual precipitation of just 2 to 10 millimeters, far less than the Sahara and dramatically lower than the Gobi. Towering sand dunes rising nearly 300 meters high, combined with daytime temperatures that can exceed 45 degrees Celsius before plunging below 10 degrees Celsius after sunset, create an environment at the very edge of survival. The Namib is not just a desert, it is the desert of deserts. In such harsh climatic conditions, the story of agriculture in Namibia has become more worrying than ever. Although deserts do not cover the entire country, the remaining land is hardly more livable. Only 2% of the national territory has sufficient water for cultivation, an extremely small figure for a country spanning nearly 824,000 kilometers square. Most rivers here appear only after heavy rainfall, which is exceedingly rare. For many months of the year, they are nothing more than dry riverbeds, offering no value for agricultural production. Namibia still practices farming, but only on a sparse scale and in complete dependence on natural conditions. The agricultural sector is currently capable of supporting only about 25 to 40% of the population, while the population itself grows at an average rate of 2% per year. This means that food demand continues to rise, while the amount of arable land remains almost unchanged. With population growth outpacing the expansion of cultivable land, Namibia has no choice but to find ways to transform barren land into fertile soil. Failing to do so, the country's agricultural sector will soon face the risk of collapse.